Okay, let's go. It's been forever. Almost forgot what some of you look like. See my glasses? Okay, since it's been forever, let's do a quick recap before we jump back into it. So, we've been talking for a while about things called matrices, which is the plural of matrix. These are just rectangular arrays of numbers. 1, 2, 3, 0, minus 1, 1. Rectangular arrays of numbers. Not very comprehensive definition, but good enough for our purposes. And we saw that we can add them. And this is done component-wise, so 1, 2, 3, 4. I can add that to 1, 0, 3, 3. And that's done component-wise. And so that's 2, 2, 6, 7. We can also multiply them by scalars. So I can take like 3 times 1, 2, 3, 4, and this is also done component-wise. Just 3 times 1, 3 times 2, 3 times 3, 3 times 4. So that would be 3, 6, 9, 12. We could also multiply them together. But this one was kind of weird. I didn't really explain to you guys why it had to be this way, but the definition for matrix multiplication was kind of different. So to multiply AB, let's say this is n by n, that is n by p. We saw that when you line up the matrices beside each other, these need to be the same to multiply. And the outer numbers tell you the size of the result. And it's done in this, strange to us because we don't really know what it's supposed to be doing. It's really a composition of functions, but that's above our pay grade at the moment. This is done by multiplying rows of the guy on the left by columns of the guys on the right, and so that's why these numbers need to match up. And so, do a quick example here, just to quickly remind you of what something like that would look like. So you could do, say, 1, 1, minus 1, 2, and you can multiply this by 1, 1, 0, 1, 3. Okay, so now you'll see here, this guy's a 2 by 2, and this guy here is a 2 by 3. So these guys are the same, so you can multiply, and you know that the result should be a 2 by 3. How do you obtain that result? Well, you take the rows of the first one, multiply every column, that becomes the rows of the result. And so we take the first row times the first column, plus 1 times 1 plus 1 times 0. First row times second column, 1 times 1 plus 1 times 1. First row times third column, 1 times minus 1 plus 1 times 3. And then once we exhaust all columns, we move to the next row. Now take the second row times all the columns, that gives us the second row. This times that, minus 1 times 1 plus 2 times 0. Second row times second column, minus 1 times 1 plus 2 times 1. Second row times third column, minus 1 times minus 1 plus 2 times 3. And that would be how we multiply the matrices. And again, Notice here, I'm doing it very algorithmically, almost like I'm a machine. I multiply things in the same order all the time, even though necessarily I don't have to, because the thing with matrices is, at any given time, you're not doing any complicated computations. It's just arithmetic. However, because you're doing so much of it all at once, it's very easy to make a mistake. It's very easy to slip up. So you want to write in patterns so that if you do make a mistake and you catch yourself, it's easy to go back and spot your mistake. Notice that everything's in line, 1, 0, 1, 0, 1, 1, 1, 1, minus 1, 3, minus 1, 3, and then all these guys would line up, right? Minus 1, 1, 1, 2, minus 1 and 1, 1 and 2, minus 1 and 1, the 1 and the 2. You do it in a certain order, and always do it in that order so that it becomes natural. You can kind of do it without even thinking about it, because that's kind of where you want to be. And so now you just simplify. So 1 plus 0, 1 plus 1, minus 1 plus 3, minus 1 plus 0, minus 1 plus 2, and minus 1 plus 6. So that will be the result of the multiplication. Okay? And of course, you can have single problems asking you to do several of these. So they can define matrices A, B, and C, and they ask, what is A times B plus C? Or something like that. So you might have to do the multiplication, then do the addition. But these were basic objects called matrices that we could do all these things with. There was also the idea of the inverse of a matrix. And this is, not every matrix has an inverse, but the only ones who have the possibility of having an inverse are the square ones. So the number of rows and the number of columns must be the same. Okay? So you can find in theory, it's possible to find the inverse of a 2 by 2 or a 3 by 3 or a 4 by 4 or 5 by 5 or n by n in general. If it's like something like this, a 2 by 3, that guy automatically does not have an inverse. You never have to search for it, it will never have one. But this guy could have one. And so the idea of an inverse is important. And so given a square matrix A, we say A has an inverse, and we use the notation A to the minus 1. It does not mean 1 divided by A. In fact, division does not exist in the land of matrices, which I've said several times. So saw people try to do it in the test. And so A inverse, A to the minus 1, and this was just notation. Do not think of it as a laws of exponents kind of thing. That's not how it works. It's just notation. It's not meant to be taken mathematically literally. So we say it has an inverse if there exists this matrix A inverse such that if I multiply A by the inverse, you will get the identity. And if I multiply the inverse by A, you will also get the identity. And we saw that you only need to check one of these, because once one is true, the other one happens to be true. That's something that we could prove, and I mentioned. So at any given time, if you want to check if one matrix is an inverse of the other, you need to check one of these two equations. It's actually a very important equation to know. At any given time, if I give you two matrices and I ask you, are these inverses? This is the equation you're going to think about. You should think about nothing else. If I give you two matrices, ask you to check, is one an inverse of the other? What you need to do is multiply them and see if you get the identity. Nothing else should come to mind. Which reminds me, that's an assignment I gave you guys back a while ago, and it seems a lot of you didn't do it. That is something you should do in general. In fact, you need to do this assignment.
What assignment?
I'm going to write it down.
But you put it on minus.
I mentioned it before. Go through notes, exams, and do the following for keywords and problem types. Write down in words in English. What you should do and what formulas apply. How and when to use it. Okay, so for example, after going through a bunch of finals, one problem that will always pop up is finding tangent lines. Right? Look at a bunch of problems on quizzes and tests. This will be something that you'll see over and over. Find the equation of the tangent line. What is the slope of the tangent line? Find the tangent line. Blah, blah, blah. Find the tangent line is a key phrase. It's a very important problem type. It shows up all the time. Meaning, whenever this shows up, you need to know exactly what to do. Right? So when you know find the tangent lines, you need to know, here's the form of the tangent line. It looks like y equals mx plus b. M is given by the derivative at the point. Use y minus y1 equals mx minus x1 once I compute the derivative to find the equation. Okay. So what you write down might not look exactly like that. Every student who does this, they will all look different. You're going to write in words that you can understand. Make sure you understand the problem type. You're going to write down what goes along with that problem type. Write down, okay, what should the answer look like? How do I find the pieces in that answer? What formula would I probably need to use in order to complete the answer, right? And maybe some other notes, right? So if you notice that, for example, you're seeing your tutor ever so often, and your tutor keeps pointing out that you keep making a certain mistake, you should probably put in a don't here. Don't do this. Whatever your mistake is. So you're going to have your do's and your don'ts, right? It's going to be personal. It's going to be for you, right? This is not some standard textbook notes. These are notes from yourself to you, right? In words that you understand. You need to write this down, okay? For every keyword, every problem type. There aren't many. Out of the 35 problems, there are just a few concepts that are tested over and over in different ways, right? So, so you can know, so find equation of tangent to y equals x squared at the point where x equals 2. So that's something like that. So then, me reading this, knowing that from my notes, I'm going to say, okay, I know I'm looking for this. And I know that m is equal to the derivative evaluated at 2. What is the derivative? Well, the derivative of that is 2x. This means that my m is going to be 2 times 2 equals 4. Now I need to find the point, because I need to be able to plug into this formula. And so I know the x value, I need to find the y value. So when x is 2, y is 2 squared, which is 4. And so now immediately y minus y1 equals mx minus x1. That's your tangent line. It's done, right? And you can even solve for, if the question requires it, you can solve for, unless it specifically states it, or it's written in mx plus b form, you can specifically write this out. This would be 4x minus 4. Right? But you should have like a strategy in your head. There's okay, if someone asks me this is what I do first, this is what I do second, this is what I do third. Here's a mistake I commonly make, I must avoid this at all costs, right? You must have a personal set of notes for you for every single keyword and problem type. There aren't many. Okay? There are a lot less than the amount of terms you guys had to memorize for your economics exam. Right? There aren't hundreds of things to memorize here. There are just tens of things, and not even the high tens of things. Okay? So something I saw repeatedly happening in the test is that I'm asking for something and people are doing something completely different. Like there are a bunch of places where I asked for the average rate of change and people started finding the derivative. The derivative is not the average rate of change. It shouldn't be in a list of things that go with average rate of change. Right? So if you happen to know that in the test, when I asked for average rate of change, you found derivative, in your notes to yourself, you need to have a line that says, don't find derivatives when asked for average rate of change. Write that note to yourself. They're different objects, right? And that was happening a lot I saw in the last test. People were they were doing something else. Like I'd ask for one thing, but they would do something for something else. So when they should be finding a derivative, they were doing the average rate of change. When they were supposed to find the average rate of change, they were finding derivatives. When they were supposed to be doing this, they were doing that instead. Like you guys clearly don't understand what needs to be done for which question. Okay? And some of your answers would have been right had that been the thing you were asking for. Yeah, if I asked you for the instantaneous rate of change, this would have been awesome. But I didn't ask for the instantaneous rate of change. I asked for the average rate of change. And for that, what you wrote is completely wrong. It's not even in the same ballpark. So make sure you do that. It needs to be done. It has to be done. There is no option. It's not, oh, it's probably a good idea. Everyone must do this. Okay. Let's continue with the recap. Where are we? I was speaking about inverses, yes. We also saw one specific formula for an inverse. We also saw the formula for the inverse of the 2 by 2. This is the only one you need to know, and it's important that you know that the formula I'm going to give you only applies to 2 by 2s. You cannot use this formula in general. So I don't like how this works. So if you have A is equal to A, B, C, D, then A inverse is equal to 1 over AD minus BC times, you swap these two, change the sign of those. And that's going to be the inverse. Provided, and this will exist, provided you're not dividing by 0 here. AD minus BC is not 0. So as long as that expression is not 0, the 2 by 2 you're looking at has an inverse. So there are times when you'll need to know how to find this formula directly. However, in a multiple choice setting, there are workarounds. So if you have a list of options, right? So let's say in multiple choice setting, and this should probably be in your notes as well that you're writing to yourself. This would probably be in your formula sheet. This is a separate thing from your formula sheet. This is actually you giving yourself a talk, right? Which is different from a formula sheet, right? A formula sheet has no context, right? You just write down a bunch of formulas. What does it mean? You need to have a separate sheet where you're given context to everything, right? Especially if you tend to be the person who is doing something else when you're asked for something else. In the multiple choice setting, if given 2 by 2 and you need the inverse. You can either use this formula or you can check the equation that gives you the identity, which in this case is the 2 by 2 identity. So maybe I should show you an example of that, even though I wasn't planning on doing it. Was there someone who found an inverse? I don't have the answer. Let me make up an example. Okay, so let's say your matrix is 1, 1, 2, minus 1, right? So, and that's your A. Now what you do is you check AD minus BC. This is this times this, minus this times that. So that gives you minus 3. So you know that your A inverse is going to be minus 1 over 3 times swap these two, change the sign of those two. That's it, that's your inverse. Okay. So the answer here is actually 1/3, 1/3, 2/3 minus 1/3. So that's the answer. So suppose you're in a situation where it's multiple choice. So it says find the inverse of A equals 1, 1, 2, minus 1. And you have options. Right? So the first one, let's say it's 2/5, 0, minus 1, 1. B, I'm going to do something that a lot of students did in the test. A lot of students will have the mistaken impression that you just take 1 over everything and that gives you the inverse. So they'll definitely have a problem that has something like that to trick people who would think that. It's not true. Another common thing is that students will think negatives, taking the negative of everything would make it inverse. Not true. Another one, they'll have something else. And then let's say in E, there's the actual answer, which out of all of these would look the weirdest to a student who has mistaken notions. Okay? Now, one thing you can do is you can either directly use the formula, like I did here, to find the answer. It shouldn't take you long. It didn't take us really long just now. And it's not. It's just finding this, swapping, and multiplying through. However, one thing you could also do is you could also do a process of elimination just by checking, right? So start here. Okay, 1, 1, 2, minus 1. Say you forget this formula. Don't freak out. You should know several ways to get to an answer. If I multiply this by the inverse, I should get the identity. Now, I would start multiplying this. I would get 1 times 2/5 plus minus 1. Now, immediately I realize that's not equal to 1. So that's not the answer, right? Because I know when I multiply, I should get 1, 0, 0, 1. So the moment the top left doesn't give me a 1, it's wrong. Move on. Right? Okay, what is this? 1, 1, 2, minus 1. Let's go with this one. 1, 1, a half, minus 1. Okay, so this will give me 1 times 1 plus a half. Oh, that's wrong. Didn't give me 1 here. Okay. And you go through this process. It won't take you long to figure out that you don't have the answer. Now, in this one, kind of mean they put the right answer all the way at the end, but still, eventually, you'll go through all these and realizing you're not getting 1, 0, 0, 1. You don't even have to finish the calculation. Once one of these is not in place, you can stop, right? So I'm only doing the top left here, and I'm not getting 1. Ignore it, move on, right? Because the inverse is when I multiply them, I must get that. And you can actually check with this one. If you multiply this by that, you will actually get this. So that equation, A times its inverse, gives you the identity, very important equation. There are times when you have to use this directly, and there are times when you can use it indirectly, like here. So normally in your formula sheet, when you're writing down finding inverses, you should write down several ways to find the inverses. If I have a 2 by 2, I can do this formula. If I have something larger, I can just check by multiplication, or I could do that in the 2 by 2 case as well. There's another way to find inverses, which technically isn't in our syllabus, but I have to remind you about row reduction before talking about it. I'll just mention it. I'm pretty sure you'll never be in a situation where you have to use it. Worst comes to worst, if you have something larger than a 2 by 2 and they're asking you to find the inverse, just do this check. Just multiply them. Multiply all the options. You should get 1s on the main diagonals and 0s everywhere else. The moment anything else like that is out of place, it's not the answer. Move on to something else. The moment you're doing something that it feels right, or it's this kind of makes sense, you're, in all likelihood, you're wrong. Right? So again, people see inverses and they see the notation, oh, it's a to the minus 1. They think put it 1 over everything. It's a very natural thing to think. It's not natural. There's a set of formulas that tells you what you're allowed to do, what you're not allowed to do. Know those things and do them or don't do them in the right context. Now, if you're just studying based on examples, you're going to confuse yourself. You're going to end up in situations where things feel like they're the right thing to do, but they're not. It's because you didn't do that assignment, and you didn't have a formula sheet that tells you what to do in each situation. Now, kind of the topic that we ended up on. Matrices can represent systems of equations, and that's where you will use them a lot. Now this is a review, so I'm not going to go over the theory and definition again, but I'll just kind of use an example to illustrate the idea. So let me pick one. And I'll reuse this example later. So let's say I'm, for example, in a 2 by 2. Although that one's kind of easy. Let's do it. Because that one I picked as an example to illustrate another idea. It's probably too easy to solve. Okay, so let's see. Something like 2x minus y 1. 3x plus 2y equals 5. So the last topic we were talking about, this is A3, section A3, which we pretty much finished. I even showed you how to find reduced or echelon form on the calculator last time. I know it's been forever, but we did it. So this is called a system of equations. It's a 2 by 2 system because it has 2 variables and 2 equations, right? Remember, we call it an n by, this is 2 by 2 system. Okay? Where the 2 here represents the number of equations, and the 2 here represents the number of variables. So if you have a 2 by 3 system, it means you have 2 equations and 3 variables. Right? So it's a 2 by 2 system. We saw that we can actually represent this via matrices by having one matrix have all the coefficients in it, the other matrix having all the variables in it, and then the other matrix having all the constants on the other side in it. This was called the matrix form of the equation. This was called the coefficient matrix. Usually denoted by A. This is called the solution matrix. Usually denoted by X with a vector or a bold X, and this is called the constant matrix. Usually represented by a vector B or bold B. So usually whenever in any exam, any context, you see something like this, they're talking about a system of equations represented by matrices. Right? that will always mean that. Anytime you see this kind of expression, you should think, oh, they're talking about a system of equations where they're thinking of it in terms of matrices, where A is going to be the coefficient matrix, that's the solution, that's the constant matrix. Right? It will always be the case. Right? Any context that guy pops up, no, that's what it means. It means they have a set of equations like this that they're thinking about like this. So that was one way in which you can represent a system with equations. Another way was what we call the augmented form. So from this, you can go to what's called the augmented form. Pretty much the idea is we kind of see where the variables are. We know that the guy on the right is a constant, so this is like a lot of writing superfluous. We see that the first column goes with the x, the second column goes with the y, and the last column would go with the constants. So we can write that in one big matrix, 2 minus 1, 3, 2. We put a line here and put 1, 5. This is called the augmented form. Right? And it's not written, but it's known that the first variable is represented by the first column, the second variable is represented by the second column. Right? So this is called an augmented form. Last time we saw also, we saw that we can actually write this into a different form, a more convenient form where we can actually get to the answers. One of these forms these are called the echelon forms. One was row echelon, one was reduced row echelon. And they have a very specific criteria that makes them that form. So we can go in and we can kind of do that here. We can get to that form using things that we call row operations, which are pretty much things we can do with matrices that will not change the solution of the system. There were 3 of them, you might recall. We can, at any given time, we can swap 2 rows. That's one row operation, that's called a type 1. We can also multiply a row by a non-zero constant. That's another row operation, that's a type 2. And we can add one row to a multiple of another row. That's type 3. So there are 3 things we can do, right? So we can swap rows at any time. We can multiply any row by a non-zero number at any time. Or we can multiply something by a constant and add it to another row at any time. Anything else you do is illegal. There are only 3 legal moves. Write that down in your notes. There are only 3 legal moves that I can do at any time, right? If you decide, oh, you know what would make this nice? I can add one to each of these and that will get it. No, that's wrong. There are only 3 things you can do. You can swap rows, multiply by a non-zero constant, or multiply one row by a constant and add it to another row. If you do anything else, it is wrong. There are only 3 legal moves. Write that down. There are only 3 legal moves. Anything else you do is wrong. You can swap rows, multiply a row by a non-zero constant, multiply one row by a constant and add it to another row. Everything else is wrong.
Can you repeat the last one?
Well, it's in your notes. This is a technical review, but so there are types. There's a type 1, swap rows. Type 2, multiply a row by a non-zero constant. And there's type 3, add a row to a multiple of another row. There's nothing else you can do when it comes to solving an equation. If you're not doing one of these 3 things, you're wrong. Okay. Now, these 3 things came from us knowing how to solve equations like we did in high school by elimination. These were the 3 kinds of things we could do to get that to happen. So we're going to do these 3 things in order to get this in a very nice form, which is called one of the echelon forms. And so for this one here, might do something like, well, I know there were things called pivots, the first non-zero number in any row. We want those to be a 1. So here, you'll notice that this, you can get a 1 by dividing through by 2. That would create fractions though, so I'd kind of hold off. I'll leave that till the end. So again, this is review. I wrote this all down, it's in your notes. So even though I know I want to eventually make this a 1, I kind of leave it for now. So leave the first row. But I know that below all the 1s, there must be 0s. So I need to find a way to eliminate that guy. So what I can do is I can do a type 2. I can multiply this guy by row 1, multiply by, say, 3. That will give me 6. This will give me -3. This will give me 3. And then I can take row 2 and multiply by -2, for example. This will give me -6, -4, -10. I just did a type 2 on both rows. Now I can add them. That's a type 3. This plus this, 0. This plus this, -7. This plus this, -7. Go back to the first row. So now I've eliminated the 0 below that. So I know this guy's going to be a pivot once I divide. This guy's also going to be a pivot. If I want reducer echelon form, I also need 0s above. So my next step should be to cancel that guy. Now if you want to kill someone, a type 3 is going to be the way to do it, because you can't multiply by 0 to eliminate somebody. So if your goal is to make someone a 0, you should be doing a type 3. So the next step would be something like, I'm being very long-winded here. Like I could finish this in 2 steps, but let's take it slow. What I can do is first rewrite this, take row 2 divided by -7 to make that a nice number. And then now I don't really have to do anything. Immediately when I add them, they will change. So this 0 I like, so I'm not doing anything to the second row. But for that one, I'm going to just add row 1 to row 2. That's a type 3. 0 plus 2 is 2, this plus that, 0, this plus that, 2. Next step, remember I want a 1 here, so at this point I would just divide through by 2. Row 1 divided by 2, and I would leave row 2 alone. Now, this is what we call reduced row echelon form. You might recall, this means that if there are any rows of 0s, they're at the bottom. We don't have those, so we don't have to worry about it. The first non-zero number in every row is a 1. These rows are called pivots. All 1s will have 0s below them as long as it's possible. That brings you into what's called row echelon form. To get to reduced row echelon form, all these 1s must also have 0s above them. This fulfills the criteria for reduced row echelon form. So, we can have a system of equations we can represent it with a matrix. We can do row operations to get it into a nice form. The point of getting it into this nice form is to talk about the answer, the solution to the system. Once it's in this nice form, each row is, again, thought of as an equation. So you'll notice here in row 2, 0, 1, 1 basically means, again, the first column goes with the x, the second column goes with the y. So 0, 1, 1 is basically saying 0x plus 1y equals 1. In other words, y equals 1 is a part of the solution. And then row 2, row 1, is basically saying 1x plus 0y equals 1, which now tells me x equals 1. Right? So, and I mentioned this last time as well, but just to remind you, start with the bottom row, work your way up. Nothing is ever random. I started at row 2 for a reason, then did row 1. Always start at the bottom row, work your way up. And so now that tells us the solution. The solution to that equation is x equals 1, y equals 1. Another way they could write that is as xy equals 1, 1. Or they could write it as 1, 1. Or they could write it as just a vertical vector, 1, 1. So these are various ways in which you can see the answer. They're pretty much saying the same thing, and obviously it's known who will correspond to who. So usually it'll either read from left to right for the variables in that order, or it will read from top to bottom for the variables in that order. So I know that this would be x, that would be y, this would be x, that would be y. And if you looked at the original equation, you can always check the original equation. So I believe that was 2x minus y equals 1 and 3x plus 2y equals 5. I plug in 1 for x and 1 for y. I get both true statements, so I know that's the answer. Which again, in the multiple choice setting, this is something that you can actually use to your advantage. So that's another thing you want to look out for. One mistake is that students completely go left field and do something that they shouldn't be doing. Another thing is sometimes they're doing the right thing, but they're doing it very inefficiently. They're doing it a longer way than they have to. So, in the multiple choice setting, if given this 2x minus y equals 1, 3x plus 2y equals 5. If you love row reduction, sure, go ahead, knock yourself out. You do that, you'll get the right answer right away. However, if they're giving you several answers, let's say they said, okay, 1, 3. Option B is minus 1, 2. Option C is 1, 1. Option D is 3, 3. Option E. Let's make this one 3. Let's be a little bit sneaky here. Let's make this a half 0. Now, why would I make that a half 0? Now, one way you can do it, again, you can go through this and you can get the answer. But another way you can do it is to just actually start plugging things in, right? Try a half 0. Okay, so you plug in the first one. 2 times a half minus 0 equals 1. Ah, that's right. Don't be so hasty. It might be a trick, right? That's why I put 1/2 0 here, right? It's important that you realize the solution to a system must solve every equation in that system. So just because it works on the first one doesn't mean anything. It must work on the second one as well. 3 times a half plus 2 times 0 is 3 over 2. No, should have gotten 5. So that's wrong. So I know that's not the answer, right? And you can go through and you can actually check. Okay, plug in a minus 1 here, that's minus 2. Minus 2, that's not 1. Okay, so that's not the answer. Plug in a 1 here, that's 2 minus 1, that's 1. Ah, okay. That's 1 check for this guy. Plug in a 1 here, that's 3 plus 2. Ah, that's 5. 2, that's the answer. Right? Even if you don't remember row reduction. Right? And that's the thing. There are so many. This is why you need to write down these phrases to yourself that I'm telling you. You need to see all the connections. There'll often be more than one way to skin a cat. And so if you know the row reduction way, given the multiple choice setting, that way is actually probably more inefficient. It's probably quicker for you to just plug in the numbers. Right? And just that's what it means to find the solution. Finding the solution doesn't mean do row echelon form. Row echelon form is just a method for finding the solution. The solution is just the set of numbers that I can plug in and make all the equations true, right? Look back in your notes when I defined the solution to an equation, that's what I told you. This is the definition. This is what it means to solve an equation. Find the set of numbers that when you plug into all equations at the same time, they're all true, right? I said this before we learned all the stuff that I just did, right? The stuff that I just did is a means to an end. If you understand the end, you understand what it's supposed to look like, there are multiple ways to get to the answer. And if you really understand what each way it involves, you will then be able to pick the most efficient one, the one that's going to save you the most time, because clock is always ticking. Okay, and I think that's where we kind of left off last time. I know it's been forever. You probably don't remember any of this, but that's where we left off last time. And I also told you how to actually find the reduced echelon form in your TI-89. So in your TI-89, if you want a matrix like, say, 1, 2, 3, 4, 5, 6, in the TI-89, you open with a square bracket. 1, comma 2, comma 3, semicolon. Okay, so you list each row, separating each number by commas. A semicolon tells it move to the next row, 4, comma 5, comma 6. And then you close brackets like that. So that's how you could write a matrix, and your TI-89 will understand that, oh, they're talking about this matrix. And there's actually a function called RREF. So what you can do is you can type this matrix, and you can use the store command to store it in a letter, and then you can say RREF of that letter, and it will show. So you can either find this in the catalog, or you can actually type it out manually. So if you forget that, oh, I don't remember how to actually access this function, I don't see it in any of the drop-down menus, you should be aware that for anything that you actually know what the command looks like, you can actually type it out manually. So you can actually use your alpha keys and type out RREF, open parentheses, and put the matrix in there, and it'll actually work as well. So, actually did a lot less. So now we're going to pick up from here. So pretty much what I want to talk about now is when you actually have a reduced Row Echelon form, how can you look at it? How is it read? And what does the different forms imply? That kind of leads to section A4, which talks about inconsistent systems and the theorem of solutions. So all that was review. Let's talk about some new ideas. Although there is some terminology that, again, is a little bit old that I'll remind you of. So we're doing A4 now, inconsistent systems. And the theorem of solutions. I'm going to tell you what the theorem of solution is. So recall, consistent. This is the phrase we use when the system has a solution. So for example, the system I had before, the 2x minus y equals 1 and the 3x plus 2y equals 5, that was a consistent system. How do I know it's consistent? I could actually find the solution. 1, comma 1 was that solution. So I could find numbers that makes it work. Whenever you can do that, we call the system consistent. Inconsistent, this means the system has no solution, which is possible. And in fact, that's what one of the things I want to talk about. I want to talk about how can you recognize when you're in one of these two situations. And then how do you follow up with that, right? So if you realize you're in the consistent way, how do you find the solution? Versus how would you know there's no solution, so stop looking for one. So, when it comes to solutions, there's a theorem of solutions. And it says the following: any system. So this is a theorem that covers any system, anything you're looking at that is a linear system of equations. Right? So the A might be of different sizes. Any system has only 3 possibilities for its solution. So the thing with linear systems of equations, there are only 3 cases to worry about. So there are only 3 possibilities. I'm going to tell you what they are. I'm going to tell you how to recognize when you're in each one. and then I'm going to tell you how to actually follow up to answer the question that might be asked about each situation. 1. The system has no solution. This is possible, okay? So, and in this case, it's called inconsistent. I'll give the examples right after this. 2. The system has one solution. This might also be referred to using the word unique. So either the system will have no solution, or it can have one solution, or we call it a unique solution. 3. And these solutions are coordinates, right? So there could be several numbers in one answer, right? Because the answer is the entire coordinate. The system has infinitely many solutions. When it comes to a linear system of equations, there is no other possibility. So if someone comes to you and say, oh, I have this linear system of equations, I found 5 answers. Here are 5 coordinates that solves this system. They have no idea what they're talking about. It's impossible to have only 5 answers. You'll either have no answers, exactly one answer, or infinitely many. There is no in between. Right? Of course, these cases are called the consistent case. So the consistent case, the cases where you have some solution, that's why I use the word some here. These are called consistent. There are 2 ways to have solutions to a system. Either there's only one coordinate that solves the system, or there's an infinite number of them. Right? And how do you even write that down? That's what we're going to talk about. Right? So your system can either have no solution, or it can have one solution, or there are an infinite number of solutions. There's no other possibility. Right? So don't let anyone trick you. Someone tell you, oh, are these 3 coordinates a solution? The solution to the system? The answer is no, obviously. Because there can't be 3. There's either 0, 1, or infinity. No other number. So let me actually illustrate. So let's look at case 1. Now I did these, already came up with some in the handouts. So here's a system with no solution. Here you have x plus y equals 3, and x plus y equals 4. Now if I have 2 numbers adding up to 3, it's also impossible for those same numbers to add up to 4. Again, it's not always that obvious, right? You'll have a bunch of equations, but sometimes you'll have a situation like this happening, right? Where you have 2 possibilities that can't possibly coexist. And so one way you can see this graphically is that these are just parallel lines that will never actually touch each other, right? So this line goes through 3, and then we have another line going through 4. But they have the same slope. There are no points in common. Now let me show you how you would recognize this if you're doing the kinds of things that we've been doing so far, like augmenting the system and finding the reducer echelon form. How would you recognize that something like this is occurring? It's actually pretty easy. There's only, when it comes to the reducer echelon form, and this is kind of why we like it, because you don't have to worry about all these things. And I mean, here, it's easy because I'm giving you only 2 variables. This is 2-dimensional. I can draw it in the xy plane. But now, once I throw in 3 variables, now we're in 3D. If I put in 4 variables, we're in 4D. You can't even imagine 4D. So this kind of thing is not always easy to come up with. Oh, I can just draw a picture and see if they never touch. Yeah, no. Once you have more than two variables, that's not easy anymore, right? But here's what's easy. You can augment the system. Here's what you'll notice. So here I would have 1, 1, 3, and I would have 1, 1, 4, right? And again, no matter how many variables I have, I just make this bigger. Conceptually, I don't need a picture. I don't need to understand what's going on. I don't need to be able to visualize it. The numbers are going to tell me exactly what's going on. Now you might want to start putting this in reduced or echelon form. So, of course, you have your pivot in the top left. You want to get zeros below that. That would be your first step. So I want to eliminate this guy. So the first thing I would do is I would leave this guy alone. And how can I eliminate that guy? Well, take row 1 minus row 2. If I want to eliminate someone to 0, I'm going to use a type 3. So I can take this minus that, 0. This minus that, 0. This minus that, minus 1. And that's how you can tell if something is inconsistent. Does anyone see what I'm talking about? Like this line here, what is it saying? Interpret that line.
It means what? Wait. It means y is equal to -1. Wait, no. It means 0 is the coefficient. 0
Yes.
equals -1. It's not.
Yeah, so this would say what? Remember the first column is the x, right? So this says 0x plus 0y equals -1. What? Impossible, right? So this line tells you it's inconsistent. And believe it or not, in every possible situation where you do not have a solution, something like that is going to show up when you start finding the reduced or echelon form. That's always going to happen. Okay? So that's how you can tell. So you can tell that there is no solution if the reduced row echelon form has a row like 0, 0, 0, all zeros except the last number, and that number is not 0, right? Because that's impossible. You can't have 0 equal some other number that's not 0, right? And every system that does not have a solution, that's going to happen. Once you start doing these calculations, you start doing those row operations to try to get it into your nice form, you'll have everyone 0 on this side except the last number. Once that situation happens, there's no solution. And so, on your multiple choice test, for example, they might give you a matrix and they might say, tell us the solution to this. This matrix represents a system, tell us the solution. And they'll give you a bunch of choices. And one of the choices might say, the system has no solution. How would you know if that's the answer you should pick? Is you look for a row that looks like this. If there's a row that has all zeros except the last number, no solution is your answer. You don't have to think about anything else. That's the only way for there not to be an answer. So that's one thing that's nice in the row echelon form way of looking at things. So this is one possibility. Here's an example of a system that has no solution. This is like case 1. So this has no solution. Now, if you drew the pictures, you'd see that, but you don't always have that option or that luxury. Let's look at case 2. One solution. Say x plus y equals 2, x minus y equals Again, this is a 2 by 2, not super hard to understand, actually not super hard to solve. I just want to use this as an illustration for you to see what's actually going on. Now, if we were to draw this picture, the second one, bring the y over, that's just y equals x, that's just a line going through the origin like that. The first one is x plus y equals 2. Remember how to draw lines. Plug in 1 equals 0 at a time. Plug in x equals 0, you get y equals 2. Plug in y equals 0, you get x equals 2. So that line goes like that. You will notice that these guys intersect at one point. So there's one point that is in common to both. That point, in fact, is the point 1, 1 in this illustration. That would be the solution. You can easily see 1 plus 1 equals 2. 1 minus 1 equals 0. So that's actually the answer. And by sketching this, I can know that's the only answer. That is a unique solution. There's no other points, right? Once you don't tell me this is 1 and 1, that's the wrong answer, right? So 2 and 3 is not going to work. A half and a half won't work. Right? I can find other numbers that would add to give me 2, and like 3 and minus 1, but that's not going to work down here. There's no other solution. And it's easy to see that from the picture. But again, you don't always have the luxury of a picture. And it's very rare that they're going to ask you about a 2 by 2. They'll ask you about something larger. So how you can figure out there's a unique solution is, let's find the reducer echelon form. Can augment this system. I know I want to make that a 0. I will leave this as is. Nice way to make that a 0 is the row 1 minus row 2. This 1 minus 1, 0. This minus that, 2. This minus that, 2. 1, 1, 2, 0, 1, 1. Here I divided row 2 by 2 to get that nice pivot. Now I know I want that to be a 0 to be in reducer echelon form. I can also get that pretty easily by subtracting. Again, row 1 minus row 2. 1 minus 0, 1, 1 minus 1, 0, 2 minus 1, 1. And then this stays. So here's how you know that is a unique solution. The left side looks like the identity matrix. That's the key phrase. Now I mentioned when you put something in reducer echelon form, and there was last time I put like a bunch of different matrices on this and we saw the reducer echelon forms, and that it didn't have to look like an identity. But when the left side looks like an identity, that's actually I2. Right? This means there's a pivot in every column for every variable. And you'll be able to say 1 times x plus 0 times everyone else is this. And 1 times y plus 0 times everyone else is that. Right? And you'll be able to say that for every single variable, because you'll have the ones lining up for every column going down. So all your variables will have an answer, and you can isolate that answer, right? The identity appears in the left. Whenever that happens, this means you have a unique solution. In fact, here, that solution is 1, 1. So that's how you have a unique solution. The entire left side, if your coefficient matrix becomes the identity, so that's another way you can look at it. The coefficient matrix A reduces to the identity. When that happens, you have a unique solution. Right? So if you find the reducer echelon form and you have a bunch of zeros and then a number that's not zero, no solution. Find the reducer echelon form, look on the left side. Is it an identity matrix? Yeah, unique solution. Case 3 is simply when neither of those situations happen. What did I do here? So let's say I had x plus y equals 3, 2, x plus 6. Again, another silly example, but in the 2 dimensions, there are only silly examples for this one. Now, graphically, if I were to graph these, this be the red line, and that be the blue line. Well, x equals 0 gets y equals 3, and y equals 0 gives x equals 3, so this goes through 3, and the lines like that. Okay. Graphing the next one, if x equals 0, I get 2y equals 6, divide both sides by 2, I get y equals 3. Plug in y equals 0, I get 2x equals 6, divide both sides by 2, I get x equals 3. So they pass through those same 2 points. And what you realize happens is, it's exactly the same line. Literally every single coordinate along this line is a solution. Right? There'll be an infinite number of solutions. Because in fact, they just looked different, but they're not different. They're actually the same line. So that's the third case you can end up in. How would you know about this case in the reducer echelon form? So, let's do the reducer echelon form. How do you know when you're in this case where there's an infinite number of solutions? Well, you augment so first thing I do is I want that to stay a 1. This guy I want to be a 0. I can do that by taking 2 row 1 minus row 2. 2 times this minus that, 0. 2 times this minus that, 0. 2 times this minus that, 0. So you end up with a row that looks something like this. Okay, so now notice it's not inconsistent. Because 0 in fact equals 0. That's not wrong. But also, you don't have the identity. So that means it's not unique. So then you can say there's infinitely many. Basically, what this is saying is that so how do you talk about the solution in this case? What would the solution be? Well, last time I wanted to find the solution, we read these solutions off. But basically, this guy gives us no information. So row 2, no info. Go to row 1, and we just get one of the equations back. So basically, that is saying that any point along on this line will be a solution. So I can put 1 comma 2 is a solution, 2 comma 1 is a solution. You know, I can put anything like 5 and this guy can be a minus 2, that's also a solution. Right? Any guy that works on that one line will solve the system. Right? Everyone that works on that line will work on the other one. Right? This is all points on this line. Will solve the solution. Solve the system. So you could put like have 1, comma 2, you could put 2, comma 1, you could put 3, comma 0, you could have 0, comma 3, you can have 5, comma minus 2, you can have 7, comma minus 4, you can have minus 4, comma 7, you can have da da da. You can have a lot of them, an infinite number in fact. Come up with any two numbers that added giving a 3, that's a solution. Now comes the question, how do you actually express this in a nice way? So we're kind of segueing into a different thing now, right? So the first thing you want to know is recognize the 3 situations. Know that there are only 3 situations. No solution, one solution, or infinite number of solutions. And know how to recognize each case. When you put them in reduced or echelon form, the no solution case will have a bunch of zeros, but there's not a 0 in the last one. That's one situation. The unique solution case will have the identity on the left side. Anything else is the infinite case, right? There are only 3 possibilities. So if you're not one of the first 2, you're one of the other ones, right? And again, drawing with lines, that kind of becomes obvious, because if you have a line and you have another line touching it once, could it touch again? No, to touch again, you'd have to curve. Once you curve, you're not a line anymore. You're not linear. You're not a linear system, right? So you'll either touch never, touch once, or once you touch more than once. Once you're 2 lines that touch twice, well, you automatically will touch more, right? Because you'll be the same line. A line can be uniquely determined by its 2 points. So there are only 3 situations, that's how you recognize it. I'll have you guys do some examples soon, but I just want to get the theory out of the way. I'm going to tell you how to write down the answers to something like that, and then we go to examples. Well, I basically summarized what I told you here in a box, a little bit shorter, to know whether it's consistent, right? So it's here, right? So you know it's inconsistent if something like that shows up. You know it's consistent if one of these 2 things happens. Right? Let's talk about how to write down the answer to something like this. And then we'll do some examples. And that would in fact be everything. Okay, then we'd be done. Not just done with this lecture, like done with everything, done with the syllabus. After this set of examples here. How to express the solution in the infinite case, infinitely many case. So this procedure, I'm going to show you with a 2x2. I'll show you again with larger things, but it's very important. Again, this is going to be one of those things that you need to write down separately in words to yourself. So we end up with a situation here. Now you need to remember the first non-zero number in any row, that was the guy we called a pivot, right? So, and you also remember that the columns represent the variables. One way you can know that you are in infinite solutions, infinitely many solutions, but it's not, of course, clearly if it's not inconsistent and it's not unique, you have infinitely many. But another telltale sign is that you will have a variable that has no pivot in its column, right? Notice that there's only one pivot in this matrix and it's in the x column, but y does not have a pivot. So here is how you can express this idea. 1, identify variables that do not have pivots. the first step. So you get to a case, you know it's not the unique solution case, and you know it has some solution because you don't have a bunch of zeros and then a number that's not 0. 2. You will set these variables, not this, set these variables equal to a parameter. Parameter is just another fancy name for set it equal to another variable. There are a couple flavors. This may be themselves. I'll talk about what the hell am I talking about here. Okay, I'll explain. I'll actually do both ways here. 3. Solve for the other variables in terms of these parameters. So in this situation, the y would get to be parameter, and what you're going to do is solve for x in terms of the y. That's all the expressions found in a coordinate. As and that's it. So let's do this. Those are the 4 steps on how to actually write down the solution. So here, I'm in blue, I'm just writing my thought process. Here, y has no pivot. So the first thing I would do is set y equal to itself. You could set it equal to another letter that's not x. But for now, let's just keep y to be itself. There are a couple ways they can do this. So for now, y has no pivot means ultimately I can't solve for it. So basically what I want to say is y can be whatever it wants. Y is y, right? The technical term for this, I think I put it in your notes. You don't need to know, but it's called a free variable. It's free to take on whatever value it wants, right? The guys with pivots are the guys you can solve for. The guys without pivots are the guys that they get to be whatever they want, and everyone else has to bend to their will, right? They're the free variables. Y is y. Okay. Now, 2. Well, I kind of did. Well, technically that was 1. That was 2. And set y equals y is actually something you would write down. So let me put that in black. Set y equals y. Now the third thing you want to do is you want to solve for everyone in terms of those variables. So you, again, go from the bottom row, work your way up. Now your row 2, no info here, because you just get 0 equals 0. So we move up to row 1. In row 1, you get x plus y equals 3. Now y is the guy that gets to be himself, so I want to solve for x in terms of y, and move the y to the other side. So here, I see that y is itself, and x is 3 minus y. Which means, how do I know a solution? Someone can just give me a y value, and I'll tell you what the x value has to be for that to be a solution. Right? So in this case, I have infinitely many solutions, and they depend, in this case, on my y value. Tell me a y coordinate, I can tell you what the x coordinate has to be to make it work. And so this leads to 4. Now you're going to express this as a coordinate as you ordinarily would, right? So you can say xy equals, you'll have 3 minus y, y. So your solution could look like this. And again, there are various forms. You could write it as a sideways coordinate, 3 minus y comma y, so that could be your solution. They could also write it as a list, x equals 3 minus y comma y equals y. That could be a solution. But now, after writing these equations out, you express the solution in a coordinate, just like that. And so that represents an infinite number of solutions because I'm not stating a specific number that has to go here. You can put any number you want here, right? Once you put a number here, it forces this number to be something, and those two numbers together will solve the system. So that's how you can express an infinite number of solutions. And that's all the theory. Let's do some examples. I'm sure you guys are tired of hearing me talk. Examples. Let's do one. That's what examples. From here, assume the variables are x1, comma, x2, comma, x3, comma, for any amount that you need. Find the solution. Two. Find the solution. Now, whenever you're given a matrix and you want to find the solution, of course the strategy is to find the reducer echelon form of the matrix. This is a little bit more complicated than you'd be required to do on the exam, so let's just take this opportunity to practice this on our calculators. You may use your TI-89 for this. I'll do it by hand on the board, but when you're doing it, you may use your TI-89. Make sure you actually know how to do it on your calculator. So if there's any kinks, work them out now as opposed to on the day of the final. I don't know how to use functions. I know I need to do, but I don't know how. Learn how now, remember for the final. To find the RREF. Now hopefully once you get to the RREF, you'll be able to actually solve the system. And here's a problem type that shows up a lot. Sometimes they'll just give you a matrix and they'll ask you to express the system, the solution to the system. Kind of like what I gave you here, but they won't even have you do any work really. They'll actually give you it in reducer echelon form. I'm still gonna have you do a little work, kill two birds with one stone, but three. Put matrix in RREF if it isn't already? And here, I'd rather you do it by hand, because these aren't complicated, and it's kind of something you should know how to do. You can use your calculator for this, but these you can, if it's not in reduced echelon form, recognize that it's not, and then by hand put it in reduced echelon form. B. Assume the matrix represents a system. Find its solution, or state that it hasn't. So there are several examples here. A 1 1 0 1 0 0 1 0 What's the last one? Give these guys 9 minutes. 1 minute per problem, see how far you can get. Most of them are 1 minute problems, especially with the fact you're using your calculator here, all of them are 1 minute problems. Again, like I said, make sure you read the handout because there I explain the common problem types that the final will give you and stuff, so on and so forth. But if you have the skills, you just don't have to worry about it. Make sure you try it. Don't wait on me to do the answer. Make sure you try. It's very important. Even if you get it wrong, it's very important that you try. Get stuck on something, what I want you to do is, as best as you can, just write down a sentence saying to yourself, why am I stuck? Oh, I'm not sure what to do with this thing. Right? You should be able to express that. So if you can't find the answer, write down what's confusing you about the answer. Oh, I'm not sure what to do with this. If you're completely drawing a blank, write that down too. Like I have no idea even how to start. That's useful. If you have no idea how to start, what that tells you is that there's a definition that you're missing. If you kind of know how to start but you're getting stuck, it means it's a technical issue. Right? So different ways of being stuck would indicate where you should go in your study. David came in, right?
Yeah.
Pajama? Liliana? Manuel came in. Did you guys get to problem 3? You guys are working over here. Got these? Okay, so you're over here on C. Okay, that's good enough. No, so let's make sure you have A and B correct. Let's actually start this. So let's do 1 and 2 over here. So 1. Right, this one, that's the identity right there. Remember that last line tells you what's on the other side of the equation. And so we're calling this x1, x2, x3. Could be x, y, and z, but just for simplicity. And so, yeah, the first equation just says 1x, and the other two is this. So here, you have x1 must be equal to minus 3, x2 must be equal to 4, and x3 must be equal to 7. Yeah, so you can pretty much read off the solution directly. Read off directly. So here you get x1 equals minus 3, x2 equals 4, x3 equals 7. Another way you can express this idea is as a vertical coordinate. Another way to express this idea is as a horizontal coordinate. The answer can be expressed in several different ways. Don't be confused either way. They can give you a list like this, or a vertical coordinate, or a horizontal coordinate. And again, these guys came from each row. So in the first one I had 1x1 plus 0x2 plus 0x3 equals minus 3. This I got from row 1, and so on and so forth. So that one was okay. You didn't really have to do anything. Just kind of read off the solutions right away. This one, you have to do some work. So I'll do this by hand, even though you won't have to do anything this large by hand, but it's something you might want to practice just to get used to the idea. But you are allowed to use your calculator for this one, so hopefully you figured out how to actually do that. So, remember reduce or echelon form. If there are any rows of zeros, they should move to the bottom. First non-zero in any row should be a 1. All ones must appear to the right of the ones that are above them, and hence they must have zeros below them. And for reduce or echelon form, they must also have zeros above them. So all these pivots, these ones, must be the only non-zero number in their column. So the strategy is start with the top left. That's the guy you want to make the pivot, which means you immediately want to eliminate this and that. Targeting something else is inefficient, not necessarily wrong, but I explained that another problem with these problems is that you can be inefficient even though you're not wrong. So the quickest way is to find the top leftmost guy, immediately eliminate guys below him. So at the moment I would leave the top one alone because this is in the position I wanted, but that I want to be a 0. How can I make that a 0? Just add them. Add what? Add what?
Add them.
You said add them?
Yeah.
I thought you said add 1. Okay. Because adding 1 to everyone is illegal, right? That's not one of the 3 rules. I just want to make sure you didn't say add 1. You can add the 2 rows, right? So you can add these together, that's 0. Add these together, minus 1. Add those together, you get 1. Add those together, you get 1. Right? And so I take row 1 plus row 2. So again, you can't get a 0 here however you want. There's only 3 legal moves. You have to do one of 3 things. You have to swap stuff, which isn't going to help you get a 0 here. Or you can multiply by a non-zero number, which isn't going to get a 0 here. Or you can add a multiple of another row to this row to create the 0. So that's the only option really. And so I can add 1 times the first row to this row, and that will make the 0 here. Okay. Similarly here, I want that to be a 0. So what I can do is I can take 2 times row 1 and add it to row 3. Right? 2 times this is 2, subtract row 3. 2 times this minus that is 0. 2 times this is minus 4 plus 1. 2 times this is 6 minus 3. 2 times this is minus 4 plus 7. Now again, it's arithmetic, so when I'm minusing a minus, I'm adding, right? Okay, you get that. So the first pivot, the top left, is established. Your next goal is to get the very next guy on the next row. If there's a pivot, get him in order, right? So now I know I want that guy to be a pivot, and obviously I want to eliminate this guy below it, because I need zeros below all the pivots. Now the pivots should be 1s. What's the easiest way to make this a positive one?
Add 2.
What do you mean add 2?
You do R1 times -1 and then add it to row 2.
Okay, that's
can't
not
use
what
that.
we would do for a couple of reasons.
Yeah.
One, if I start using row 1 to fix something here, I'm going to eliminate this 0 that I worked so hard to create. Because if I multiply this by -1 and add it here, now this 0 is going to disappear. I want that 0. So I'm not allowed to do anything that will affect that 0. That being said, knowing that I want to keep this 0, that sort of tells me if I'm using another row, row 3 would be the one I want to use. Right? So I would never use row 1 to fix anything in row 2, because that's going to kill the 0 that I worked for. So if I want to use another row to do something, it's definitely row 3 is what I'm
Wait,
going
but
to use.
can't you use, multiply the second row by -1/2?
By -1,
1/2.
why 1/2? Multiply
Wait, by
this by
negative-
-1/2?
I'm sorry, by 1.
By -1?
Yeah, by -1.
Yes, that would be the best way to do it. Take row 2, multiply by -1. Right. That's one of the 3 things that you can legally do, and it's the easiest one to apply here. I don't need to add another row to anything. Multiply by -1 makes it what I want. So that works. And so this is established, that is established. I need this to be a 0. So how do I get this to be a 0?
Multiply the second row by 3
Mhm.
and then subtract.
Yeah, you can do that. 3 times row 2 minus row 3. So it's good. You want to have practice on seeing these things. What am I allowed to do? And what's the best way to get something that I want to happen? So yeah, multiply this by 3, I get a -3. So, well, multiply this by 3, subtract that, I get 0. The 0 stays, which is good. Multiply this by 3, I get -3, subtract that, 0. Multiply this by 3, subtract that, 0. Multiply this by 3, subtract that, 0. So now I end up with a row of zeros. Now, technically we could stop here and solve the system, but let's actually go a little further. Now I have all the pivots, the row of zeros at the bottom. First non-zero number in every row is a 1. The 1s appear to the right of the guys above them. We have zeros below. This is in what we call row echelon form. To get reduced row echelon form, I now need to eliminate that guy. So that's my next goal, right? What's the easiest way to eliminate that guy? Using one of the 3 legal moves.
We have to use the last row, right?
Well, the last row has a bunch of zeros, so that's not going to help me with anything. Right, the last row now has no power to change anything. He's all
What about
zeros.
the second row? Like, can you multiply the second row by 2?
Multiply by 2 to make this a 2 and then add it.
Yeah.
Yeah. So I can take row 1 and add it to 2 times row 2. That would create a 0 here. So 1 plus 2 times 0 is 1, minus 2 plus 2 times that is 0, 3 plus 2 times that, 1, this plus 2 times that is minus 3. So when you plugged into your calculator for the RREF, what did it tell you?
I got this, but the last solution for the top row, I got -4, not negative.
Me too.
That's where it got you.
Negative 4?
Yeah.
Did we make a mistake somewhere? Well, let's quickly run over this. We just added the first 2 rows. So here, if you make a mistake, you can actually go back and check it. So here, I added the first 2. 0, minus 1, 1, 1. That's right. Here, 2 times this, minus that. 2 minus 2 is 0. 2
I think
times
what
this.
happened was the first row you left it the same, but when you rewrote it, it's -1 instead of being -2,
Oh, yeah.
perhaps.
Right where you're,
Oh, yeah, that's actually just, I miscopied. Yeah, 'cause I didn't do anything to that guy. So, and I still didn't do anything to him at this point. So at this point, that would be a negative 4. So, if this were me, I'd write a note to myself. Make sure you cover the down rows correctly, come on. Just that's a note to myself, right? Especially if I realize I made that mistake like twice, nah, that's too often. At that point, I'm gonna use red ink on my formula sheet. Make sure, double check when you're just copying down rows that you're copying the right thing. That'll be a note to myself. Okay, so this is the reduced Row Echelon form, okay? Now, you guys should be able to plug this into your TIE and it'll give you that right away. Now that we have that, how would I write the solution? So remember that this is for the variable x1, x2, x3. And so the line obviously is here. How do you start to do it? So what's the first thing you do?
see which ones, are what.
See which ones don't have pivots. So here is a pivot, here is a pivot. Those are only 2, which means in this column there is no pivot. X3 does not have a pivot. So my first rule, first action is to set X3 equal to itself. Now I'm going to start from the bottom row up and solve for everyone in terms of X3. Row 3 gives us no information, so I immediately move to row 2. Row 2 tells me that X2 minus X3 is equal to -1. This means that my X2 is going to be X3 minus 1. So that is X2 solved for in terms of X3. Move up to row 1. Row 1 tells me that X1 plus X3 is equal to -4. So I'd be able to solve for X1. I would be able to get minus X3 minus 4. And so that is my solution. The solution is X3 is itself, X2 is X3 minus 1, and X1 is minus X3 minus 4. Or they can write this horizontally. So minus X3 minus 4, X3 minus 1, and X3. So that would be the solution. Identify the guys that don't have pivots, set them equal to themselves. Start from the bottom row, working your way up, solve for every other variable in terms of those variables, and then you just place them in their position in the coordinate. And so that would be what this solution looks like. Notice you have an infinitely many solutions here. because for every possible value someone comes up for x3, you can find a coordinate that will work with that value. Okay? So if someone says, oh, x3 equals 1. Okay, well, minus 5, comma 0, comma 1 will solve that system. Right? X3 equals 2. Okay, minus 6 plus comma 1, comma 2 will solve that system. Right? Anytime they tell you a value for x3, you can determine these two values that will solve whatever system this was representing. Now move on to 3. A. So this is already an RREF. Any row of zeros is at the bottom. First non-zero number in any row would be a 1. All 1s appear to the right of the guys above them, and the 1s are the only zeros in their column. So that's this guy right here. This guy's the pivot. And he's the only one, and then you have everything satisfied. Which means that that represents a system that is in reducer echelon form. So I can call this x1, x2, x3, and that's where the equal sign will show up. So now that we know that, how would we actually find the solution? Right?
So I got x1 equals negative x2 plus 1.
What is the first thing you do?
Identify the x1, so. Oh, well, the ones that don't have.
The ones that don't.
Yeah.
So there are 2 of them.
Ah.
So your first order of business is to set those guys equal to themselves. x2 equals x2, x3 equals x3. And so now, all you do is you go through the rows and you solve for everyone in terms of those. So in the first row, you see x1 plus x2 equals 1. This means that your x1 is 1 minus x2. So that tells you what the solution is. Your x1 is 1 minus x2, comma, your x2 is itself, comma, your x3 is itself. That's your solution. So in this case, people have to pick 2 numbers, right? Tell me what x2 and x3 are, and I can tell you a whole coordinate that will solve your system. There'll be an infinite number of them. Right, so one thing I want to mention, they rarely do this, but I've seen it done before, so I just want to mention it. Sometimes, for whatever reason, they might call these guys some other variables. So in the event that that happens, don't let it confuse you. Sometimes you may use other variables as parameters. It's rare, but I've seen it, so let's just make sure that if it shows up, we know how to deal with it. So, for example, they could say set x2 equals t, right? So they came up with the letter t. And set x3 equals r. For whatever reason, they picked these 2 letters to represent these guys. And so then, in your row 1, you would have x1 plus x2 equals 1. So your x1 is equal to 1 minus x2. But your x2, they called it t. And so the solution could be written as 1 minus t, comma r. If you see a solution expressed like that, it shouldn't confuse you. You should just realize, oh, what they did was they called x2 t and they called x3 r, and so they solved for x1 in terms of those guys. But that's it. Once it's in reducer echelon form, identify the guys who do not have pivots, set them equal to themselves, and then run through all the equations and solve for everyone else in terms of those guys and write them in your coordinates. So let's look at B. Okay, so in B, it's in RREF. Don't have to do anything in that regard. Any row of zeros at the bottom, first non-zero number in each row is a 1. All ones that appear to the right of the ones that are above it, and all ones are the only, these ones are the only non-zero numbers in their column. Therefore, this is reduced Row Echelon form. Notice that this is a pivot, that's a pivot, which means the third column, no pivot. So if this is x1, x2, x3, I would set x3 equal to itself. Now, going to row 2, I get x2 equals 3. That's just what x2 is. Going to row 1, I get x1 plus x3 equals 2. This means x1 is equal to 2 minus x3. This means the solution is 2 minus x3, comma 3, comma x3. So that would be your answer. Okay, so every now and then, a variable will have a specific number for its value, but everyone else can change values.
Yeah.
But again, you don't have to worry about that situation specifically. If you just go through the strategy, go through the 4 steps that I tell you, you'll end up falling into the right answer. Identify the guys with no pivots, set them equal to themselves, solve for everyone in terms of these guys, put them in coordinates. Whatever you end up with is the answer. Right? So don't be weirded out that that's a 3. It doesn't matter. That's a 3. We follow the right procedures. Now this guy, of course, is not in RRE.
This one you want fractions, is what, because you automatically go into fractions. Right?
Yeah. So I would kind of avoid that. Remember, we leave the fractions until the very last step. So at the moment I leave this as a 2, then I want to kill this guy. So how can I do that?
Multiply the top row by 2.
Right, row 1, take 2 times that and add it to row 2. So 2 times this is 4, and add it to that gives me the 0. 2 times this is minus 2, add it to that, 0. 2 times this is positive 6, add it to that, 0. 2 times this is 2, add it to that, 5. So what's this answer going to be?
So that's inconsistent.
Right, no solution. Right? We ended up in that situation where we had all zeros except the last number. That makes no sense, right? That says x1 plus x2 plus x3 equals 5, impossible. This system has no solution.
Is that in RREF?
What, this?
Yeah.
No.
No.
To get it in RREF, I would, at this point I can divide by 2. I can divide, so the RREF for this would look like 1 minus a half, 3 over 2, a half. And this would, I can divide through by 5. That would be the RREF technically. But at this point, again, a part of the goal is to solve the system. The moment I see something like this happening, I know there's no solution. Yeah, so I wouldn't get fractions in the beginning, so I would leave it, but if the goal is to get to the reduced Row Echelon form, I would save it for the last step to actually divide through by that system.
Oh, yeah.
Okay, D's a big one. So this is like your x1, x2, x3, x4, and the equation will show up here. Even though they don't always write that, so just be aware that they're not always going to put the bar there for you. They expect you to know that the bar is going to be to the far right. Okay, is this an RREF? It's an RREF, it's already reduced. How do I know? There's a criteria. Any row of zeros appear at the bottom. The first non-zero number in every row is a 1. All these ones appear to the right of the ones that are above them. All these ones have zeros below them. And for reduced, that's row echelon form. For reduced echelon form, they will also have zeros above them. So this is actually pretty reduced. This is reduced echelon form. So now, what do? Well, of course, we identify the pivots for the sake of identifying who does not have it. Here I can see x3 does not have a pivot in its column. Set x3 equal to itself or some other letter. They might do that, don't let it confuse you. Then start from the bottom row up. Row 4 gives us no information, so immediately move to row 3. Row 3 tells me that x4 is equal to 1. Move up to row 2. Row 2 tells me that x2 plus 3x3 is equal to 11. So my x2 is going to be 11 minus 3x3, and that's my x2. Move up to row 1. Row 1 tells me x1 plus 5x3 is equal to minus 2. So that means x1 is equal to minus 2 minus 5x3. That's my x1. And so my solution is going to be x1 comma x2 comma x3, which is just itself, comma x4, which is a 1. So that's the solution. Right. So again, see, if you know what you're looking for, it's not difficult. But you have to know what you're looking for. So you have to take the time to write down the strategy, write down in words what you should do in first, second, third, and memorize that. Know it like the back of your hand. Practice a bunch of problems until it becomes natural for you to do this. Okay, so this one is already also reduced. Again, zero rows are at the bottom, there are none. First non-zero number in every row is a 1. The ones that appear to the right of the ones that are above them. There's only zeros in their column. It's in reduced echelon form. So this is x1, that's x2, that's x3, that's x4. And so I have a pivot here and here, which means x2 and x4 does not have pivots. First set x2 equals to itself, set x4 equals to itself. Those guys are free variables, they can be what they want. Start from the bottom row moving up. Row 2 tells me that x3 plus 2x4 equals 0. This means that my x3 is minus 2x4. Move up to row 1. This tells me that x1 minus 2x2 plus x4 equals 1. This means that my x1 is equal to 1 plus 2x2 minus x4. So therefore the solution is 1 plus 2x2 minus x4, comma, x2, comma, minus 2x4, comma, x4. F3, 6, 2, 1, 3, 4. Actually, probably. Make sure you're talking about the right thing, Jhevon. 1, 1, minus 1. See, I caught myself. I made sure to double check before I moved on. See that? 1, 3, 4. Should maybe space these out more. So 2, 2, 2, 1, 3, 4, and 3, 6, 2, 1, 1, minus 1. Okay, those are the last two examples. not in reduced row echelon form. I know I want a 1 up here. Quickest way to do that is actually to swap the rows. So that's what I would do. Move row 2 to the top. And I know I'm immediately going to want a 0 here. Quickest way to get a 0 is to, in the original, take row 1 and subtract 3 row 2. And so this minus 3 gives me 0. This minus 3 gives me 3. This plus 3 gives me 5. So that would be the first step. Now I know ultimately I want this to be a 0. So what I can do is I can take 3 row 1 minus row 2. 3 times this minus 0 is 3. 3 times this minus 3 is 0. 3 times this minus that is minus 8. At this point it's pretty reduced. I would just divide through by 3 in each row. Divide through by 3, 1, 0, minus 8 over 3. Divide through by 3, 0, 1, 5 over 3. So notice that I waited until the last step before I made fractions. And at this point, now you see this actually looks like a 2 by 2 identity. This has a unique solution. So here it's my x1, x2 is actually equal to minus 8 over 3, comma 5 over 3. So this is a unique solution situation. What about this one?
You can swap the row.
You could swap? But if I want a 0 here, how would I get it? So I'm going to move row 2 up to the top. How would I get a 0?
Multiply first row by 2 and then subtract.
So, and I'm referring, my labels here refer to the previous step. So technically here I want to multiply row 2 by 2 and then subtract row 1.
Yeah.
Okay, so this times 2 minus that, give me 0. This times 2 is 6 minus that. This times 2 is 8 minus that. So that's the first step. Now I want this guy to be a 0. How can I get that to happen? There are ways, I can even make this a little smaller, right? Do a little trickery here. Divide by 2, just throw that in. So this will actually give me 2 comma 3. Be a little nicer. How do you do that?
You have to multiply both.
Sure.
Them by opposite. So
Yeah.
the first one by 2,
So row 1 times 2,
and then the second row by 3.
and then row 2 by 3. So now these are the same, we can say subtract, right? So take the new row 1 minus the row 2, 2 minus 0, 2, this minus this, 0, this minus that, minus 1. And let me put this back. At this point, one more step and we can get these guys to be 1s. So this is row 1 divided by 2, row 2 divided by 2. And again, here we have a unique solution. X1, x2 is equal to minus that, 3 over 2. That was a long lecture, but we're done. That's it. That's all we need to know. So technically, you know how to do every problem on every final now. You have all the knowledge that you'll ever need to get an A in this class. This was the last thing you needed. So Take a breather, maybe a slightly longer one, maybe like 15 minutes, and then we'll come back here to start from the beginning, quote unquote.